in example 5 here, they're asking us to complete the square again, this time with a negative leading coefficient. And it says find the area of the region bounded by the graph of this function, the x-axis and the lines, x is 3/2 and x is 9/4. So here's x is 3/2, x is 9/4. Here is our curve above. We want to find the area under that curve, since this that curve is positive across our entire interval. And we want to find out which of the formulas this will sort of fit into. But this one is very different looking, because in that denominator we have 3x minus x squared. And you know, we usually have just one term under there that has the x variable in it. Usually our a value is just a number. It doesn't have x in it at all. And they did give us the hint in the right after the word example. It does say complete the square with a negative leading coefficient. First, let's set up our integral. We want, let me switch colors too. This is the definite integral from 3/2 to 9/4 of our function, 1 divided by this quantity square rooted 3x minus x squared dx. So now I can get this out of the way a little. And we got to work under that radical to have it fit one of our formats. So we're going to complete the square. Complete the square. And what is under that radical is 3x minus x squared. And if we rewrote that in descending order, it would be negative x squared plus 3x. And to do this technique, let's factor that negative out for now. So we got to factor a negative out. Negative x squared minus 3x. Alright, and we're ready to work on completing the square. So that format says take half of this middle term and square it. So if I take half of 3, it's going to be 3/2 quantity squared. And let me rewrite that as 3/2 quantity squared. And if we add it here, we're also going to subtract it. So we're going to have a minus 3/2 squared. We've added and subtracted the same quantity, so basically we've done nothing but help get it in a format where we can complete the square. So we're going to have negative. What's our quantity squared? Well, it's going to be x minus 3/2. X minus 3/2 quantity squared. And then we have our minus 3/2 squared. And let's write that as 9/4. Or no, let's leave it as 3/2 squared. Alright, and to get everything back, let's distribute this negative through there again, and we will reverse our terms. So this negative is going to go to this negative, that's going to become a positive 3/2 quantity squared, minus this quantity x minus 3/2 squared, and we're done with completing the square. What we found right here can replace what we have here underneath the radical. So I'm going to rewrite this definite integral with that substitution. Our integral goes from 3/2 to 9/4. Let's see, let's move the dx up top. Dx is our numerator. And now underneath that radical, we're going to have this. 3/2 quantity squared minus the quantity x minus 3/2 all squared. Yeah, I guess we're ready then to, let me clean out this complete the square stuff. We're ready to plug this into the Arcsin formula, because we have our dx up top. And we think about this, you know, our u is going to be x minus 3/2, and our du, the derivative of that would be 1 dx. So du and dx are interchangeable, and we're ready to do the antiderivative. So this is going to be the arcsine of up top, we're going to have our u value, x minus 3 halves. Our denominator is our a value, 3 halves. And remember, this is a definite integral from 3 halves to 9/4. And maybe to make this easier to actually evaluate, we have this divided by 3 halves. That's like multiplying by 2/3. So arcsine of 2/3 times the quantity x minus 3 halves from 3 halves to 9/4. So let's evaluate. The 9/4 drops in first. So our first term is going to be the arcsine 2/3 times. In the parentheses, we're going to have a 9/4 minus, let's rewrite this with a common denominator, 6/4. And then we're going to evaluate our lower limit, plug in the 3 halves. When the 3 halves goes in, we're going to have 3 halves minus 3 halves is 0, times 2/3 is 0, so it's the arcsine of 0. And in these parentheses, 9/4 minus 6/4 is 3/4. So this is all going to become a 3/4. And the 3's will cancel, and we're left with a 2/4, which reduces to a half. So we have the arcsine of a half minus the arcsine of 0. Think back to the unit circle. The arcsine is a half. The sine of what angle gives us a value of 1/2? Well, that's pi/6. Minus what is the arcsine of 0? Well, that's 0. So we get pi/6, which is approximately 0.524. So here's a review of the basic integration rules, we have so far, and it's quite a good list. There's a lot going on there. We have our power rule, exponentials, our trig functions, and these new arcsine, arctan, and arcsecant ones. These would be pretty good to have memorized for the AP test if you plan on taking that. And remember, these are the basic integration rules. If you're going on to calculus in college, if you take calculus 2, that entire course is mostly more advanced integration techniques. Now let's compare some different types of problems. A big part is recognizing, what format it fits and how to actually do the antiderivative. If we look at the first one, they all look pretty similar. Let's just compare all of them. In the first one here, we have an x in the denominator in front of the radical. In part B, that x has moved up top, and it's x times dx in the numerator. Completely changes the dynamic of the problem. In part C, that x is nowhere to be found. We just have our dx up top, and our denominator is the radical with x squared minus 1 under it. So these are all pretty close, and each requires a different technique to integrate. Maybe the hard part is figuring out which one is which. If we check out that first one, it looks like it's going to fit the arcsecant pattern. We have this out front. We have something underneath the radical. Here is our u. This is u quantity squared minus 1 squared. So it is going to fit that basic arcsecant pattern. So this antiderivative is going to be the arcsecant of the absolute value of x plus our arbitrary constant. Now, what happens when that x moves up to the numerator? Well, this looks like just a sort of a power rule situation. If our u is equal to x squared minus 1, then our du would equal 2x dx. Well, we have an x dx, we're missing a 2, we would have to balance it with a 1/2, and now we have u to the negative 1/2 power du. And when we perform that antiderivative, we're going to wind up with, well, let's just write it out. We have our 1/2 definite integral u to the negative 1/2 du. So we would antiderive and get u to the positive 1/2 divided by the new power 1/2, or times 2. So that would cancel out there, and we're just left with u to the 1/2 plus c. And our u value was x squared plus 1, so it's x squared plus 1 to the half power, or we put it under a radical, excuse me, that's a minus 1, plus c. So first we used an inverse trig function, then it was just a basic u substitution. What about the last one? We could ponder it for a while, but I'll tell you right now, that's not going to fit any of our patterns. We cannot find this using our presently known techniques. There is a way out there to do it, but we haven't gotten there yet. So for now, part C we cannot do. Example 7, comparing integration problems. Find as many of the following integrals as you can using the formulas and techniques we've studied so far in the text. So everything is wide open. And all these look, they all got logs in them. Something's going on here. First we have our x ln of x in the denominator. In part B, it's ln of x is now in the numerator. Part C, it's just the ln of x dx. So, what can we do with the first one? It might help if we broke it apart a little bit. We could rewrite that as 1 over x times dx over ln of x. That wouldn't hurt, right? Pulling it apart into two separate terms like that. And then we could look at this as being a term just multiplied by the numerator. So we could have the antiderivative of 1 over x all over the ln of x dx. Now that should starting to be looking like something's going on. What is the derivative of the ln of x? Well, that basic derivative is 1 over x. So it looks like here we have our denominator is a function u. Our numerator is its derivative u prime. Does that ring any bells? Well, yeah, that's our natural log. When we take that antiderivative, it's going to be the ln of that denominator plus c, or the ln of the absolute value of the ln of x plus c, the natural log of the absolute value of the natural log of x plus c. And let me rewrite that without all the scratch work in the way. The ln of the ln of x absolute plus c. Okay, let's see what we can do with letter B. Now that ln of x is in the numerator. So I could sort of drag this denominator x out as a 1 over x ln of x dx. So it looks like here's an inner function, u. What's the derivative of the ln of x? 1 over x dx. So there is our du. So what we have is u to the first du. And when we take the antiderivative, it's going to be u to the 1 power up divided by that new power, or times a half. U to the 1/2, or 1/2 u squared plus c. And then, of course, we replace our u back with our u sub, which was the ln of x. 1/2 the ln of x quantity squared plus c. So first we had a natural log. Well, let me write it over here. This was a log rule. This was a straight up power rule. Now how about the last one? The definite integral, or the antiderivative of the natural log of x dx. This is something we can't do with present techniques. Now note, grab that. In the last two examples, 6 and 7, it was the simplest form of the function were the ones that we cannot integrate. Here we got rid of the x altogether, and it's just the simple natural log of x. That's the one we could not perform yet. Same thing back here was part C. It was the simplest one without that extra x variable thrown in, which actually made it to be the hardest, if not impossible, to find the antiderivative of. And that ends section 5.8, the inverse trig functions, and that is the end of chapter 5.